In the previous lecture, we saw that the convolutional result which we got by sliding a kernel function over the input matrix was smaller than the input matrix. How do you get a convolutional result that is the same size as the input? Now, when you apply a convolutional filter over an input image or an input set of neurons, there are some other decisions that you need to make which will affect the convolution result. One is, what is the size of the convolution result that you want? Do you want the result to be smaller than the original image or larger or the same size? The second is, when you slide your function in sliding window fashion, how many cells should you skip each time you slide over? These decisions involve zero padding and stride size. Depending on the relative sizes of the input and the convolution result, you can have narrow versus wide convolution. Let's take two examples here. What you see in green below is the actual image, and what you see in purple is the convolution result. The input matrix is the image that you feed into your convolutional layer. So the layer at the bottom is the input matrix, that is the layer which comes first, and the layer at the top is the convolutional result, that is the result of applying a kernel to the input matrix. What you see on the left is called narrow convolution. This is because the output layer is narrower or smaller than the input. There is no zero padding to the input. Whatever cells are present in the input, those are the only cells that we consider when we slide our kernel function over the layer. What you see on the right is wide convolution. This is the input matrix at the bottom is narrower than the convolutional result, or rather, the convolutional result is wider. In order to get a wider convolutional result, the input has to be zero padded along all edges. When the output is wider than the input, it's wide convolution, and we need lots of zero padding. The example that we saw earlier when we first understood convolution had no zero padding. We considered the input 6 by 6 matrix as is. We slid a 3 by 3 kernel over the 6 by 6 matrix and got a convolution result which was 4 by 4. The convolution result is narrower or smaller than our input matrix. This was a narrow convolution with no zero padding. Zero padding refers to the input matrix. We haven't added an additional layer of zeros around the edges of the input. Let's say we change the input matrix to include some zero padding such that our 6 by 6 matrix has now been converted to a 10 by 10 matrix with two layers or two rows and two columns of zero padding along all its edges. Now, if we consider a 3 by 3 kernel and slid it over this input matrix in the same fashion that we did before by skipping just one row or one column of cells at a time, that is with a stride of 1, our convolution result would be an 8 by 8 matrix. Our original 6 by 6 matrix has produced a convolution result that is 8 by 8. This is wide convolution, which we can achieve using zero padding. We can get a larger convolutional result if we apply more zero padding to our input matrix. We convert our 6 by 6 matrix to a 12 by 12 matrix by adding 3 rows and 3 columns on all of our edges of our original matrix. We'll get a convolutional result of a 10 by 10. This is, of course, assuming a 3 by 3 kernel function with a stride of 1. That's the number of rows and columns it skips when it slides over the input matrix. The more zero padding that you add, the wider our convolution will be. The advantage of zero padding is that every element of the input matrix will pass through the filter at least once. If you haven't zero padded, and depending on your stride size, you might end up missing some of the elements at the very edge of your matrix. With zero padding, that should not occur. The decision of whether you want to zero pad your inputs or not depends on you based on what size you want your convolution result to be. If you want a convolution result that is larger than the input, then you'll decide to zero pad. Another design decision when you set up your filter or your kernel function is how will you slide it over the input matrix? How many columns you'll skip when you stride horizontally, and how many rows will you skip when you stride vertically? What you just saw was a horizontal stride of 1. This is the stride that we used in our example convolution. When we moved downwards, that is the vertical stride. In our example earlier, our vertical stride was 1 as well. Each of these you can vary independently. You can have a horizontal stride of 2, a vertical stride of 3, and so on. The stride size, either horizontally or vertically, determines how much of your local receptive field will overlap when you go from one neuron to another. A smaller stride size means greater overlap, and this stride size is a very important hyperparameter when you're training your convolutional neural networks. In order to get a convolutional result the same size as the input, you need to zero pad the input. This means you'll add layers, that is, rows and columns of zeros to all edges of the input matrix. And when you slide your kernel function over, it'll include these zeros as well in the convolution.